So question one here, we want to know which of the following is or not a conjugate acid-base pair. So we have these different pairs of species. We want to know which of the ones are not an acid-base pair. Select all that apply. And so just to give you, and this goes back to the Bronsted-Lowry definition of an acid and a base. Again, Bronsted-Lowry acid donates a proton. Bronsted-Lowry base accepts a proton. And so the conjugate acid-base pair only differ by one proton. So if you look at the formula of each species in the pair, if they only differ by one proton, it's a conjugate acid-base pair. That means everything else is the same, except one of them has one extra proton than the other. So now if we take a look at these, we see H2CO3 and HCO3 minus. The only difference between these two species is that HCO3 minus has one less proton. So that is a conjugate acid-base pair. Now again, whenever you remove a proton, you add a negative sign to that species. Whenever you add a proton, you add a positive sign to the overall charge of that species. Next we go to H2PO4 minus and PO4 minus. So here if we look at both of these species, you see they differ by more than one proton. So this would not be a conjugate acid-base pair because again they differ by more than one proton, so it doesn't meet the qualifications for a conjugate acid-base pair. Next we have H3O plus and H2O. So again, these two species only differ by one proton, so therefore it would be a conjugate acid-base pair. Next we go to SO2, SO3 2 minus. Here there's no protons, so this is not a conjugate acid-base pair. You got to have protons on at least the conjugate acid for it to be a conjugate acid-base pair. And likewise, the formulas differ by one oxygen. So again, this doesn't meet the criteria for a conjugate acid-base pair. Next we have HCN, CN minus. The formulas differ by one proton, so this would be a conjugate acid-base pair. Next we have C6H5COONA. This is actually what we call sodium benzoate. And we have C6H5COO minus. So these do not differ by one hydrogen. They differ by sodium. So this one would not be a conjugate acid-base pair. And then lastly, we have HClO3, ClO3 minus. This differs by one proton, so this would be a conjugate acid-base pair. So in this question, we want you to write the conjugate acid or the base for the following species. So again, with conjugate acid, add a proton to the formula. So when you add a proton to the formula, you're going to add a positive charge to the overall species. Now that species was negative, when you add a positive charge, it would become less negative. And to write the conjugate base, remove a proton So that's how we do the two. So we want to write a conjugate acid. We add a proton to the formula, add a positive charge to the overall charge. To write the conjugate base, we remove a proton from the formula. We add a negative charge to the overall charge. So in A, we want to write the conjugate acid of NH3. So we're going to add a proton. At the same time, we're going to add a positive charge. So this would be NH4 plus. So all you have to do when you type it in is type NH4 plus, all as one string of characters, and that would be the answer. Conjugate base of HSO3 minus. So to get the conjugate base of HSO3 minus, we're going to remove a proton. When we remove a proton, we add a negative charge to the overall charge. So the conjugate base would be SO3 2 minus. Conjugate acid of C3H5COO minus. So what we're going to do to make the conjugate acid, we're going to add a proton and a positive charge to this species. And so we get C3H5COOH. Lastly, we want to write the conjugate acid and conjugate base for HSO4 minus. So to write the conjugate acid, we add a proton to this and a positive charge. So the conjugate acid is H2SO4. For the conjugate base, we remove a proton and add a negative charge. So the conjugate base would be SO4 2 minus. So you see here HSO4 can donate a proton or it can accept a proton. So when you have species like that, those are called amphoteric species. They can behave as an acid, a Bronsted-Lowry acid or a Bronsted-Lowry base. So it can go either way. And again, those are called amphoteric species. And if you've watched the other videos or in your book, you may come across that term. So for example, water is amphoteric as well, because water can either donate a proton and become OH minus, or it can accept a proton and become H3O plus. So with organic acids, you need to write it as C3H5COOH because that H is the acidic proton. These other H's are attached to carbon, which are not the acidic proton. So that's why we write it as C3H5COOH, because that H is attached to an oxygen. So not all hydrogens are created equally. So those hydrogens attached to carbon are not involved in being donated. Only the hydrogen attached to oxygen is involved in being donated. Oh, I forgot that one. So here we want to calculate the pH of a solution. And there are two categories of acids that we can calculate the pH for and two categories of bases. So with the first category is strong acid and a strong base. So when you're calculating the pH of a strong acid or a strong base, it's just whatever the hydroxide ion concentration is or the hydronium ion concentration is, we can directly calculate the pH. Now the other category is weak acids and weak bases, and for those it's a little bit different. But in all four of these examples, we have either a strong acid or a strong base. Now the strong acids, there are 6 common strong acids, so make sure you know those. It's in the book, it's on PowerPoint, etc. So with the strong acids, the concentration of the acid equals the concentration of protons as long as there's a one-to-one relationship between the proton and the formula of the acid. Same way with strong bases. Strong bases are going to be your soluble hydroxides. So as long as there's a one-to-one relationship between the formula and the hydroxide in the formula, the concentration of the hydroxide compound equals the concentration of hydroxide. When it's not one-to-one, as we'll see in example D, we have to do an extra step. So when we're calculating the pH of a strong acid or a strong base solution, we're going to use one of these two equations. pH equals the negative log of hydronium ion concentration, or POH, negative log of the hydroxide ion concentration. And what we have to remember is that the pH plus POH equals 14. Now there's different ways you can approach doing these problems. I'm going to do it one way, but if you did it a different way and get the same answer, no worries. So here we have a 0.0035 molar solution of perchloric acid. Perchloric acid is a strong acid, so we simply just plug in the concentration of HClO4 because you notice there's one proton for every one molecule or one formula unit of HClO4. And so the pH is 2.46. Next we go to B. We have a 0.05 molar solution of sodium hydroxide. So here we first have to calculate the pOH because we're given the concentration of hydroxide, and notice one hydroxide ion for each formula unit of sodium hydroxide. Once we find the pOH, we subtract it from 14 and get the pH. So the pH is around 12.7. In C again, it gives us the hydroxide ion concentration. We find the pOH and then subtract it from 14 to get the pH, so 8.58. Now in D, notice that here the ratio of hydroxide to one formula unit is 2 to 1. So there's going to be twice as many hydroxide ions as there are formula units of strontium hydroxide. So that's why in the first step, we multiply the concentration of strontium hydroxide by 2 to get the actual concentration of hydroxide. And then we calculate the pOH and then subtract it from 14 to get the pH. So that's the one thing you have to watch out for strong acids and strong bases, is make sure the ratio is 1 to 1, or if it's 2 to 1, you have to account for double the hydroxide ion concentration. So on the previous slide, we had to calculate the pH of a strong acid or base. Here we want to calculate the pH of a weak acid. And the way we know this is a weak acid is, well, A, it's not one of the 6 common strong acids. But even if you didn't know that, B, you see that it gives us the Ka. So the Ka is the equilibrium constant for that acid. And you see it's very weak as well, 10 to the negative 8. So if it gives you the Ka, is a good indication that you're dealing with a weak acid. So how do we calculate the pH of a weak acid? So first off, we will have to write the equilibrium equation for the dissociation of the weak acid. So here we have HClO, we have H2O. HClO donates a proton to water, and we get ClO minus and H3O plus. So HClO and ClO minus are conjugate acid-base pairs, and H2O and H3O plus are conjugate acid-base pairs. Now what do we have to do? We have to do similar to what we did in chapter 17 when we were dealing with equilibrium. We have to use the ICE table. So this should all look very familiar. So we have our initial concentration of acid. We have none of the products. So we're going to lose acid and gain products. And at equilibrium, this is what we have. So you're thinking, oh no, quadratic equation. Well, it's okay, because if you notice, the Ka is 10 to the negative 8. The initial concentration is 10 to the negative 3. So here we can use the approximation by canceling this minus x on the concentration of the acid. Because it's going to be so small x, it's not going to cause a significant change to it. And you can check this by the 5% rule. As long as x is less than 5%, you're okay. So we're going to do this because, again, initial concentration 10 to the negative 3, Ka is 10 to the negative 8. So we set up our expression. Remember, products over reactants, so x times x over 0.0045 equals Ka. We combine like terms, we get x squared equals 1.305 times 10 to the negative 10, take the square root, and this equals the equilibrium concentration of H3O plus. Once we have that, we simply just take the negative log of that and we get a pH of 4.94. And that's how you calculate the pH of a weak acid solution. Now, another thing with weak acids is because since they're weak electrolytes, they do not fully dissociate like strong acids or strong bases, so we can calculate what's called the percent ionization. So percent ionization is telling us what percent of the reactant actually ionized into products. So again, we can do this for weak acids and weak bases because it's only a small percentage of the overall concentration of the weak acid. Now with strong acids, it would be almost 100% ionization because those are strong electrolytes. So again, it gives us the initial concentration of the weak acid. It gives us the Ka, so butanoic acid. We write the dissociation of butanoic acid again. The acid donates the proton to the water, and we get the conjugate base of the acid and H3O+. So again, we set up our ice table. Initial concentration is 0.02. We're always going to lose reactants and gain products. So we get 0.02 minus X and plus X at equilibrium. So if you notice, the concentration of our weak acid is a lot greater than the Ka. So here we can do the approximation and remove the minus X from the equilibrium concentration of the weak acid. So now we set it up. We have Ka equals X times X over 0.02. We get X squared equals 3.02 times 10 to the negative 7. And we get X here as 5.50 times 10 to the negative 4. And this is the equilibrium concentration of hydronium ions. So this is how much of the weak acid actually ionized. So to find the percent ionization, we take the equilibrium concentration of the weak acid and divide it by the initial concentration of weak acid times 100. And we get about 2.7%. So again, it's the equilibrium concentration of H3O plus divided by the initial concentration of weak acid times 100 gives you the percent ionization. And you see here it's less than 5%, so the approximation was valid. If it was greater than 5%, you'd have to go back and do the quadratic equation. So in this example, we have a 0.003 molar solution of HA, and HA is just some general weak acid, and it is 0.205% ionized. What is the Ka of this acid? So in this example, we're looking for the Ka of this weak acid. So again, we're going to draw the equilibrium equation. So HA donates a proton to water. We get A minus and H3O plus. We do the ice table, and this should be 0.3. And we get our equilibrium concentration. Now notice here that the percent ionized is 0.2%. So that's less than 5%. So we can negate the minus X because it's less than 5%. So now Ka equals X squared over 0.003. So in order to solve for Ka, we need to know what the equilibrium concentration is for A minus and H3O plus. So once we know that, we can calculate Ka. So again, percent ionization is equal to the hydronium ion concentration at equilibrium divided by the initial concentration of weak acid times 100. Well, we know the percent ionization, so we can find the hydronium ion concentration. So we set it up, and we get the hydronium ion concentration at equilibrium is 6.15 times 10 to the negative 6. So we plug this in for X, and we get the Ka, which is about 1.3 times 10 to the negative 8. And so that's how we use percent ionization and the molar concentration of initial acid to solve for the Ka. You could also do this if it gave you the pH of the solution. So with the pH of solution, you can find the hydronium ion concentration and then find the Ka.